Okay, good morning to all of you. I welcomes to all in our lecture series on statistical mechanics, that is your core paper 14, belongs to 6th semester BSc syllabus. In our last class we have been discussed about microstate and macrostate, how it is important to observe the physical dynamics of the ensemble or of a system, that we have been discussed. And before that we have been discussed a basic idea about the probability permutation combination, and we have been considered an example for distinguishable particle two compartments. This is the table line corresponding macrostate. These are the macrostates, and corresponding microstates are these one. Okay, and then in detail we have been discussed. Okay, you have to follow on the previous lecture this video. Okay, so here we found in general the total number of microstates will be c to the power n. C means number of compartments, n will be total number of particles. And by considering different examples, at last we found that thermodynamical probability, that is n1, n2, n3 in general, nk will be n factorial by n1 factorial into n2 factorial into n3 factorial up to nk factorial. Okay, here a k is the kth compartment. Okay, and or it can be written as summation over I equal to 1 to k ni. This is n is nothing but a total particle. That these things we have been discussed in detail, and if you are going to consider thermodynamical probability, then it will be probability of macrostate, then thermodynamic probability divided by total number of microstate. Total number of microstate will be c to the power n. For this case the c will be k, so k to the power n. Okay, so these things we have been discussed in detail, and today we have to discuss your relation between entropy and thermodynamic probability. I told that this is very much important topic. Okay, so carefully you have to watch, and accordingly you have to write in your note by pausing the video. So here entropy is represented by S, is a physical or thermodynamical parameter, or also it is called as the extensive parameter. How it is extensive, that we are going to discuss later. So here entropy is a physical or thermodynamical parameter of a system which provides the spreadness of the particles in the system. Some book they have been written in the language of disorder, scattered of the particle, spreadness. Somewhere it is written spreadness of the particle, disorderness of the particle, scatterness of the particles. Okay, so and just before we have been discussed thermodynamical probability is the number of possible microstates of a particular macrostate. That means in our previous lecture we have been discussed that thermodynamical probability W is nothing but number of possible microstates of a particular macrostate. So these are the basic definition you can say about entropy and thermodynamic probability. Now we are going to find out the relation, how these two are related. To know the relation between S and W, here we have considered a simple system having three compartments, contains three identical but distinguishable particles. Identical means size may be equal, but this may be red, this may be green, this may be blue. That means it can be identifiable. That means identical, but it is going to be distinguished from one to another, red, green, blue, like that. So here is the system, and it is divided into three equal compartments, 1 2 3. This is c1, c2, c3, and three particles, distinguishable particles, are a, b, c. So this is the example we have been taken to understand the relation between S and W. Okay, so here I am going to correlate that this system is nothing but suppose you consider a gas cylinder in which three particles or three molecules, three different molecules are there. A, B, C. Okay. So now we have to find out the microstates of corresponding macrostates, and we are going to be judge, or we are going to observe the spreadness and disorder scatterness of the particle. Okay, it is interesting somehow. You just watch. Here you can see that total number of microstates will be 3 to the 3, because 3 is the number of compartments and 3 is the number of particles. So 3 to the 3 will be 27 microstates we are going to be get from the arrangement of these 3 into these 3 compartments. So here we are going to find out the microstates of different possible macrostates and then relate with entropy, that is nothing but your spreadness or disorderness. Okay, carefully you have to observe. First, I have been evaluated all the microstates of the corresponding macrostate. Okay, suppose first we have to consider 300. 300 is a one macrostate, means all the 3 particle will be in the first compartment, second compartment will be 0 particle, third compartment will be 0. That means the situation will be this one. All the 3 particles will be here, first compartment, and the second, third is going to be vacant. So for this situation, the number of microstates will be 1, 3 factorial. We know that W300 will be 3 factorial by 3 factorial and 0 factorial into 0 factorial. Here 3 factorial is the total number of particles. Okay, total number of particles by 3 factorial, 0 factorial and 0 factorial. So it is W1. Let consider it is W1, first macrostate. How many microstates possible for this macrostate? It will be only 1. Okay. Now consider the second macrostate, that will be 030. That means all the 3 particles will be in this second compartment. How many possible arrangements? Also 1. That means for this macrostate, how many microstates are possible? Only 1. Right. Now consider 003. How many microstates we can get? Only 1. That means arrangement of 3 particles will be in the third compartment only. That means all the 3 particles will be in the third compartment only. First one, second one is vacant. Okay. Now consider this one, fourth macrostate. 210. That means 2 number of particles will be in the first compartments and 1 particle in the second compartment. How many numbers of arrangements? It will be 3 factorial by 2 factorial into 1 factorial into 0 factorial. That will be number of ways of arrangement will be 3. See here, A B C can be possible, A C B can be possible, B C A can be possible. So these 3 arrangements are to be possible for this corresponding macrostate. That means 3 microstates are possible for this macrostate. Okay, so here you can observe that the spreadness of the particles inside the cylinder. So here for these 3 cases, that means for 300, 030, 003, all the 3 particles are in the same compartment, one compartment. Here all the particle in one compartment, all the particle in the one compartment, right? But in case of 210, here you can see only 2 particles are in the first compartment, another particle is in the second compartment. That means spreadness is somewhat increased. Spreadness means distribution of these 3 particles inside this gas cylinder. So here previously it was vacant, this area, this volume is vacant, this volume is vacant, but now in this case, for this macrostate, this volume is filled by a particle or molecule. Okay, the spreadness is increased. Similarly, if you are going to consider W5, another macrostate, that is your 120, then also for this macrostate we are going to get the 3 microstates. These are the 3 microstates. Okay, so the spreadness of this one and this one is same, but the spreadness of this one and this one, if I am going to consider spreadness of this and this spreadness is larger than this one. Okay, if I am going to compare this cylinder and this cylinder, the spreadness of the particle or gas molecule is more in this cylinder as compared with this cylinder. Okay, that means here microstate increases, that means your spreadness also increases. Here microstates is 1, here microstates is 3. Now another possible macrostate is 0 to 1. That means the first compartment will be 0, filled by 0 particle, and the second compartment will be 2 and the third compartment will be 1. The possible arrangement will be these 3. Okay, and the next one will be 0, 1, 2. Possible macrostate I am telling. For this microstates also will be 3. For this macrostate 1, 0, 2 also microstates will be 3. Okay, so another macrostate, that is your 2, 0, 3. The possible microstates are also 3. So here you can see that if we are going to consider the macrostate, these are the macro. Okay, these are the macro states: 4, W4, W5, W6, W7, W8 and W9. Up to W9, it is W9. W9 macrostates, all the macrostates have 3 number of microstates. So from your W4 to W9, whatever we are going to consider the macrostate, each of the macrostate have 3 microstates, and all the microstates spreadness is same. That means if I am going to compare this one, the spreadness is similar, the spreadness is similar. That means any one of the microstates we are going to be compare here, any one of the microstate, the spreadness or the disorderness is same. But if we are going to compare any one of these microstates, any one of them, suppose this one, any one of these microstates is going to compare any one of these 3 microstate, then we can found this microstate have large spreadness as compared with this one. Okay, so in other way we can say that here the microstates is larger than corresponding these microstates. So if we are going to consider either omega 1, omega 2, omega 3, the microstates are 1, 1 and 1. If we are going to consider the microstates of W4 to W9 macrostate, then all have 3 microstates. Okay, so each microstates have equal spreadness, but if we are going to compare this one, then the spreadness is increased as compared with this one. Corresponding microstates also increased. Okay, so here microstate increased, spreadness also increased. Now we have to consider last possible macrostate, that is your W10. I named it is W10, is your 1, 1, 1. That means in each compartment only one particle or molecule has to be present. What will the possible microstates or arrangements? These are the possible arrangements. These are the 6 possible arrangements: ABC, SCB, BAC, BCA, CAB and CBA. So that means 6 microstates will be possible, or you can say 6 arrangements are possible. So here microstates are increased. If we are going to compare previous macrostate and corresponding microstate, here for this microstates are increased. Okay, if we are going to consider the spreadness of the particle or molecule for this macrostate and compare, I am going to compare the spreadness of the particles of this macrostate and this macrostate. You can see that Suppose you have consider this one and compare with this one. Here spreadness is large. Here in all the directions, in all the way particles are there. That means in the first compartment particle is there, second compartment, third compartment also particle is there. Particles are equally spreaded over the total volume of the cylinder, but here it is not so. Here it can be found that second compartment is vacant, only first compartment is filled, last compartment is filled. That means this volume is vacant, but in this case all the volume equally filled by the molecules. That means the spreadness of the molecule has been increased, or you can say disorderness has been increased, or you can say scatteredness of the particles or molecules has been increased for this macrostate which have large microstates. So here we have been conclude one thing, that whenever microstates are increased, corresponding disorderness, or you can say scatteredness, or you can say spreadness of the particle or molecule has been also increased. So hence this is nothing but your W, and this spreadness is nothing but is represented by the entropy. So this W increases, spreadness also increases. That means both are directly proportional with each other. So here I drawn a graph for you. From this we can easily analyze the whatever the result we found. Here W1, W2 up to W10, all the macrostates. This side has been represented the values of microstates. Okay, for W1 it is 1, microstates are 1. W2 up to W3 microstates are 1. Okay, from W1 to W3 microstates are 1 1 1. Then from W4 to W9 the value is 3 3 3. We got the microstates 3 3 3 3. So this axis is represents the values of microstates, number of microstates. Here you just write number of microstates, it will better. Okay, number of microstates of corresponding macrostates. Okay, and this side is represents spreadness or disorderness or entropy. So you can see that from macrostate from W1 to W2, whatever the spreadness, here it has been increased. For W4 to W9 somewhat increases, and for W10 it has further increased. So up to W, from W1 to W2, this dotted line represents the entropy. Okay, entropy, and this dark line represents the number of microstates, variation of number of microstates with respect to your macrostate. So for the macrostates W1, W2, W3, suppose this much value, suppose this much value is your disorderness. Suppose let this is value is anything, suppose it is any whatever maybe, suppose this much. But for W4 to W9 it has been further increased. You can see it has been further increased, the spreadness. If I am going to compare this obviously spreadness increases. Suppose it has been increased from here to here, suppose increased. Then if you are going to consider W10 last one, then the spreadness has been further increased. So here you can see that whenever the microstates are increased, corresponding disorderness also increased from this graph. So from this graph it can be found that when numbers of microstates or thermodynamic probability of a macrostate increases, the corresponding spreadness or disorderness, or it is called as the entropy of the three particles system. Here we are considering three particles increases in the system. Okay, hence S, your entropy is proportional to W. So whenever we have considered a actual gas, means suppose we are considered only three particles. So actual gas means suppose you consider actual one cylinder. Inside this cylinder large number of particles will be present, large number of compartments can be established. So for that W thermodynamic probability will be so large. So it will be convenient to write ln w instead of omega. Hence, S is proportional to ln w. Here one thing you have to remember, whenever large number of particles you are going to deal, no, suppose large number 10 to the power 23, like that, Avogadro number of particles, that type of particle whenever you are going to be deal, at that time those particles has to be represented in the graphically in ln format, ln of n, like that. Then the variation of the graph can be perceivable, otherwise it could not be analyzable from the graph, the variation of particle and its corresponding property. So whenever the large number of particle we are going to consider, at that time we have to take log. If we are going to take log, then it will be easily distinguishable, distinct variation, or all the variation in the graph can be easily extractable. Okay, so whenever large, you just remember, now you have to just remember, whenever the large number of particles we are going to be considered, at that time instead of writing those numbers, we have to write ln that number. So ln w instead of writing w, so s proportional to ln w. Okay, so here we conclude that entropy is proportional to thermodynamical probability, or the so-called number of microstates. Okay, so here another example for you I have done just for the discussion, or we have to just our clarification of this statement, that is your s proportional to omega. You just watch. Okay, we found that s proportional to omega, ln omega, or S equal to K, Boltzmann constant. This is Boltzmann constant, K ln W. How it is? It is, there is a proof. That proof is not in your course, so no need here. So S equal to K, it can be instead of ln, natural logarithmic, that is log E, log base E W. Okay. In this format it has been written in some book. In this format also written in some books. So to verify, or to analyze, or to perceive much more about S is proportional to ln W or omega, here is the another example. You just watch. So you can verify. I not drawn the figures like this. You can draw in your rough. So here you just verify. You can verify this relation by considering 4 particles and 4 compartments in the system. So here is the 4 compartment. Okay, A, B, C, D are the 4 distinct particles. Okay, so in this case microstates will be 256 microstates. It is not possible that you in our here to draw this type of microstates. So I'm going to write only numbers. Just what I'm going to write the numbers of the each macrostates. So it is very large, but you can try in your rough. No, here I already done for you. No need to do. You just write whatever I have written over here. So here I am writing only the macrostates and corresponding microstates without drawing. Okay, drawing I am not going to do, because if I am going to do the drawings, then it will be so so large. So here we are going to consider, this is the first macrostate W004. That means 4 factorial, 4 number, total number of particles are 4. 4 by 0 factorial, 0 factorial, 0 factorial into 4 factorial will be 1. So here is 4 will be there. That can be. That means you just see that, suppose here 4 is there. 4 means all the particles will be in the 4th compartment. This is 3rd compartment. This is 2nd compartment. 1st compartment. So in the 4th compartment, all the particles will be present. So what will the microstates? It will be 1. Let all the particles will be in the 3rd compartment. That is your macrostate is your 0040. Also it will be 1. Likewise, whenever all the particles will be in a certain compartment, then the microstates will be 1. So suppose we are going to consider W04 means all the particles in 2nd compartment, 00, and other 2 are, or the other 3 are vacant. So how many microstates? It will be 1. W4000, that means all the particles in the 1st compartment, and other 3 are vacant, also 0. And okay, now we have to consider W0013, that means third compartment will be contain one particle, fourth compartment will be contain three particles. So it will be 4 factorial by 0 factorial, 0 factorial, 1 factorial, 3 factorial, it will be 4, right? Then I'm just alternating the positions. 3 1, if 1 3, 3 1, also 4, 3 here, 3 1, that means second compartment 3 particle, third compartment 1 particle, also 4. W01, here I just altered the position, 1 particle 3 particle, the 0 1 0 1 3 0, also 4. 0 W1300, 4 W3100. Here 3 1 means first compartment 3, second compartment is your 1, okay, and other are vacant. So here W1030 means first compartment 1, second compartment vacant, third compartment 3, fourth compartment vacant, also will be 4. That means 4 factorial by 1 factorial, 0 factorial, 3 factorial, 0 factorial, also 4. Then W3010 will be 4, W0301 also 4. Here I done some, here I forgot two things, after that I haven't written. So the numbering you have to do accordingly, okay. 12 13, here you have to do, this one will be 14, this one will be 15, okay. I forgot at the time of writing note, and then after I haven't written these two, so this numbering are not correct. So after 13, here you have to write 14 and 15, okay. So these two star marks should be 14 and 15, then this will be 16 17, like that, okay. So it will be W3001 will be 4, W1003 also 1, sorry 4, then W0103 it will be 4. So up to this much 1 3, that means one compartment will be contain 1, another compartment will be contain 3. The possible arrangements are this one, up to this much, from 5 to this much, okay. So these are all the macro states have 4 microstates, okay. Now we have to consider another arrangement, that is your 0 0 2 2. That means third fourth is going to be filled by 2 particles, and other first second is going to vacate. Then how many ways it will be? That will be 4 by 0 factorial, 0 factorial, 2 factorial into 2 factorial, though it will be 6. So here last two third fourth will be 2 2. This is called so called macrostate, and corresponding microstate is this one. So the other arrangements are W0220, also can be 2200, 2020, 0202, and 202002, okay. Up to this much we have that any two compartments are going to be filled, any two compartments see, any two compartments are going to be filled by 2 particles, and other are going to be vacant. And these are the possible macrostates, and all the macrostates having the corresponding microstates are 6 6 6 6 6, okay. So here also you just correct the numbering, okay. This is your 13 means 14 15 16 17 18 19 20 21 22, like that you have to correct. 22, this will be 23 24, like that, okay. Then we have to consider 2110, this type of arrangement. One compartment is going to be filled by 2 particle, and another 2 is going to be filled by 2 like this, and another will be vacant like this. That means suppose here A B C D, this will be vacant, okay. This type of macrostate, how many numbers is possible? Here you can see W1210 can be possible, W1120 can be possible, W2101, W1201, W1102, W2011, W1021. These are all are the different here different macrostates, okay. And corresponding microstate will be, see, number of particle in 4 factorial, by 2 factorial into 1 factorial into 1 factorial into 0 factorial will be 12. And if you are going to find out this one, microstates of this macro state, also you are going to get 12. You just check 4 factorial by 1 factorial into 2 factorial into 1 factorial, also 12. Like all the macro states has to be have corresponding microstates are 12 12 12, and other uh, and another 4 uh, collections will be there. These are W1012 can be possible, W0112, W0121, 0211. So up to this much, all the microstates have macrostate. All the macrostates having microstates are 12 12 12. Okay, and last one is, so total will be 35. Okay, whenever you are going to be count, total numbering is 35. Total numbering, total number of possible macrostates will be 35. You just, whenever you are going to correctly number. Okay, so when W1111 will be 4 factorial by 1 factorial 1 factorial 1 factorial. So for this type of macrostate, what are the possible microstate? 24 different arrangements are possible for this macrostate. So anyone, for if you are going to consider this macrostate, 12 number of microstates, 12 number of different arrangements are possible, like that. So if you are going to be add, see here, 1 2 3 4. So 1 into 4 is equal to 4. Then here you can see 1 2 3 4 5 6 7 8 9 10 11 12. 12 fours are there. 12 4 into 12 is equal to 48. How many 6 are there? 1 2 3 4 5 6. 6 sixes are there. So 6 into 6. 6 into 6 equal to 36. Then 12 12s are there. See, 1 2 3 4 5 6 7 8. These are 4. 12. So 12 into 12 equal to 144. Then this one is the last one is 24. 24. So total is 256 microstates will be 256 microstates. So if generalized way, if we are going to try to find out, that will be 4 to the 4 also 256. So now these are the macrostates we have been just written. The question is that for which macrostate S is maximum, that is spreadness is maximum. Okay, see, each macrostate there is some spreadness, but from one macro to another macro the spreadness is going to be changed. So from these all the arrangements, if we are going to consider all the macrostates, which macrostate S is maximum or spreading is maximum? The answer is here. The macrostate for which large number of microstate is present, that is W1111. In case of W111, any type of arrangement we are going to consider. See, for this W1111 24 arrangements, see, this is one arrangement I have been shown. This can be, you can say this will be A C B D, like that. Then you can say A B C D, like that. 24 arrangements are possible, but any arrangement you have to going to take, or macrostate, this one having 24 microstates. For this macrostate has large number of microstates, that means this macrostate is most this macrostate has maximum spreading. Maximum spreading means maximum entropy also we can say. For this macrostate, maximum entropy or maximum spreadness or maximum number of microstates are possible. Okay, so this macrostate also called the most probable state. Here I written. So if I am going to drop 4 ABCD 4 particles from the above into this box having 4 compartments, then the most probable state will be this one ABCD. That means each compartment is going to be filled by one particle. That may be ABCD, that may be ACBD, that may be ABCD, any one of the 4, any one of the 24. Okay, but whenever we are going to drop 4 particles inside the container or box having 4 compartments, the most probable state will be this one. That means all the each of the compartment is going to be filled by one particles. That is your most probable state. The most probable state also called as equilibrium state. Equilibrium state. So at this state, equilibrium state or most probable state, what is the maximum? Spreadness is the maximum. If spreadness is the maximum, also entropy is the maximum. So that for, see, up to this much you have to write. Up to this, I don't have had space, only for that I adjustly I have been written, but you have to write serially. Okay, you have to write up to this much, then you have to write this much, then you have to write this much. Okay, then after you have to write. So at equilibrium, S is maximum, entropy is maximum, that will be equal to K ln W max. Okay, for this case, when W, that means thermodynamical probability, will be maximum, at that time we are going to find out the maximum entropy. So at this can be possible at the equilibrium. Okay, so at the equilibrium we are going to get the most probable state. Whenever we are going to get the most probable state, or the easy state, or the most accessible state, or we can say that the system wants to stay in that state, that is your most probable state. The most probable state, that is nothing but is your so-called equilibrium state. So equilibrium state is nothing but called as the most probable state. At the most probable state, the spreadness is maximum. Spreadness is maximum means entropy is maximum. So it can be written as entropy max at equilibrium. Entropy maximum subscript. Okay, maximum is written in subscript, is equal to K ln W maximum. Okay, so write down the note up to this much. Whatever we have been discussed, you have to write down. And in the next class we are going to discuss additive nature of entropy and increase of entropy during expansion, then increase of entropy by diffusion of gas. Okay, so thank you so much for watching this video. You just write down the note, and this relation S direct proportional to W, S direct proportional to ln W, this relation is most needed for us in our forthcoming lectures. Okay, so thank you so much for watching this video. Thank you.